So let's move on to the next presentation. So this is coming from Cosimo Gerardi from Treason. Cosimo is CTO of Treason, and he's exactly presenting what's expected out of him. Like Treason has really established a gigawatt factory. And then since I was also attendee of the silicon heterojunction workshop in November, I also had the opportunity to see this gigantic factory really. So it was very nice to see the factory, but I think Cosimo will more focus on experiences of Treason in scaling up heterojunction technology into this gigawatt scale. Cosimo, the floor is yours.
Okay, thank you. I'm sharing the presentation.
Perfect.
Okay, thank you for inviting me. I'm very, let's say, proud to participate to this event. I'm Cosimo Gerardi. I'm CTO of Treason, the European Gigafactory, and I will speak about our experience in scaling up the production of heterojunction technology. Treason is the largest European factory in Europe with a full capacity of 3 gigawatts per year. And it is in Sicily, in Catania, in a place that we call Etna Valley, because it's there is a location of let's say, concentration of semiconductor technology industries. And our activity is strongly committed to research and development. First of all, we were among the first developing heterojunction in the past and increasing the R&D on heterojunction to improve the efficiency and reducing costs. But we are also working a lot on developing tandem technology in collaboration with the CNS, the French Technology Center of Chambéry. And for this, we are a European leader in the photovoltaic manufacturing. We have, in our factory, we are a company from Green Power, and our mother company has invested around 1 billion of euros, including CapEx and OpEx. And we received about 190 million euros from European Commission, Italian government, Innovation Fund, and Italian Contratto di Sviluppo. And we will have a 3 gigawatt full capacity. Will arrive at a maximum of 1,000 direct jobs and other 1,000 indirect jobs created in Sicily, in Italy, in the south of Italy. So with this factory, we aim to reshore a resilient PV supply chain in Europe. In Europe, we are concentrating to produce mostly for European market, in which there is a good scenario in terms of expected growth in the market. We expect that the annual production will even double in 2027. And for this reason, we are strongly committed to produce module for Europe, but not only at utility scale as in the past, but also looking at the residential or mostly at the commercial industrial application. We are perfectly aligned with the European Commission initiatives that has launched the initiative to reduce the dependence from non-European supplier, but at least 30%. And Treason is the first European PV gigafactory fully in line with this initiative. And in addition, we are focusing on the innovative technology of heterojunction. Our history, we started in 2010 as a joint venture between Green Power, ST Microelectronics from Semiconductor, and Sharp, producing thin film technology. So we have a long history from amorphous silicon manufacturing. In the meanwhile, Treason was fully owned by Green Power, and as today we are fully owned by Green Power. And in around 2017, we decided to design a new factory, heterojunction factories, to let's say remove the thin film tools and start with the production of 200 megawatt of heterojunction cell and module that started in 2018. Since 2018, we have produced until the end of 2021, beginning 2022, with achieving high efficiency and producing modules, especially for utility scale, for our mother company that were installed in a utility scale plant. In 2022, it was decided to expand the factory, or factor 15, and we have started the construction of new building, introducing new tools, and expanding to 3 gigawatt. So in 2023, we started with the first prototypes of our products, and we have started with production in September 2024. And we are, let's say, today we have all the tools here for the 3 gigawatt. We are completing the expansion to 3 gigawatt, and we will grow gradually, reaching the gigawatt scale in the next year, and then expanding up until our maximum, that is 3 gigawatt per year. This is the factory. The existing building was A, B, and D, in which we produced 200 megawatt. Then we decided to introduce the new tool in the building B, in which we produce the cells. And we introduced a new PECVD, PVD, screen printer, and so on, tools for the cell production. And in the building C was completely new, 50,000 square meters of building for module assembly, in which we have 5 assembly line of 600 megawatt capacity each. The full area is 150,000 square meters. Some numbers. 3 gigawatt is in Europe is quite a huge number. We will produce 5 million of modules per year, 14,000 modules produced per day, which means 300 million solar cells produced per year, 800,000 solar cells per day, and renewable energy of 5.5 terawatt per hour produced, and so 25 million tons of CO2 that will be avoided in 10 years. So it's a very huge number in Europe. We are the only gigafactory in Europe, and I think also the only big factory in Europe that produces not only modules but also cells. Our factory is state of the art, is a very it's a smart factory with intelligent manufacturing using high automation control, fully control automation and tracking, in which we can also control for each step the quality of the production, and this can ensure a good quality of the product, using artificial intelligence and using usage of data with complex data like computer vision, binning optimization, but also predictive maintenance. It's very important, the usage of a large number of images. We use imaging not only for visible light, but also including electroluminescence, but also photoluminescence, in which we can have a correlation. The photoluminescence maps is very well connected with the efficiency of the solar cells. This is our first product. We started producing in September. We achieved also the certification from TÜV Rheinland, and these are the first pallet that have been produced, and we will continue our production. By today, we are using the first line of 600 megawatt. We will expand to the second line by the end of the year, and so on. We continue reaching the gigawatt in the next year. We have focused on heterojunction. Heterojunction technology is a technology that we know very well because we started working several years ago. We know that heterojunction has high performances, and it is a low temperature process. That means that can preserve the quality of the silicon, have a good mechanical properties, and also for us it's important to know that this low temperature process is compatible with other low temperature process like the tandem technology. We have a reduced number of process steps. Is very important for automatic factory. A high control of the manufacturing is very important, and we can have we have few tool per process, and this means we can have a good control of the manufacturing. And also we have a long history by producing our module. We have our high quality, and we can have reliable modules compared with the competition. This is what I said about the manufacturing. This is for me is a very important aspect, because we have a quite limited number of steps, and this means simplify the manufacturing process, use better automation, and avoid any, let's say, manual handling or even let's say that can reduce the reliability and the performance of the cell. The process is never exceed 200 degrees, means that we can have a very good quality of wafers. So we can reduce the thickness even to less than 100 micron, like also how other companies are doing today. But for us, it's important that we can reduce the consumption of silicon. And for us, also another important aspect that we are focusing on a low temperature process, and in the future we will develop also tandem technology, that is another low temperature process, and we can increase the compatibility with the assembly. Some results from our modules that we have produced, we can demonstrate that we can have even 3 times the requirement from the IC norm for damp heat test and thermal cycle tests, and very important also the point of that, for example, we have some outdoor installation. This is important installation in Chile, in Atacama Desert, so in very harsh environment with high amount of UV and quite harsh environment. Comparison with the conventional PERC with the 3 main supplier from PERC technology, we show continuously we have a higher energy. This is 1 year of production, and also in the last workshop that we held in Catania, in the silicon heterojunction workshop from Atomos Tech, it was shown that this trend is continued until 2024. So confirming that we have a good production even in a very harsh environment. Let's say, focusing on technology, as already been told by Keining in the opening session, we have in the opening talk, it is important the attention to the wafers. We can reduce the thickness, but we can use also cheaper wafer, because of in the future we expect to have, let's say, some reduction of cost, especially because we don't heterojunction is less, let's say, is less impacted by oxygen concentration. This means that because of the low temperature process of the solar cells manufacturing. The other important aspect is the amorphous silicon and its let's say evolution with nanocrystalline silicon, inducing also silicon suboxide layer. It's very important to improve the selection of the contact, and also improve the quality of the interface and the quality of TCO by improving the mobility and reducing the free carrier absorption. Another important aspect is the metallization. Metallization is important for heterojunction, because for the low temperature, heterojunction is strongly impacted by the consumption of silver. And so it's important that the industry that is focusing on heterojunction can reduce the amount of the consumption of silver, introducing silver copper. Heterojunction as a TCO means that TCO is a good barrier against copper. So in principle, copper metallization can be used better in heterojunction. We are working a lot on metallization, in introducing silver copper paste, and studying also the development for copper plating. Other important aspect that has been already mentioned by previously are the assembly, because we want to let's say remove all the silver from the assembling. We are going to to the next step, that is the zero bus bar technology, so reducing the silver consumption on the cell, but also introducing a new assembly tools that allow us to reduce as much as possible the silver consumption. And then also using UV protection encapsulant, using downshifting, like it has been showed by the other companies. First of all, the improving of the amorphous silicon by introducing nanocrystalline silicon. This is an example for the P-type. The P-type, introducing the nanocrystalline P-type layer, we can improve the efficiency, but the nanocrystalline N-type in the top and the P-type nanocrystalline in the bottom, we can increase the collection path of holes, for example, and so we can, as been shown recently, we can, in general, with heterojunction, it is possible to improve the efficiency, as also some record obtained in literature show that this can achieve very high efficiency. Another important aspect is the TCO. We are working with our suppliers von Arden to optimize TCO by increasing the mobility and reducing the free carrier absorption. So there are several, let's say, supplier of TCO with the development with important materials, but also the PVD tools is very important. Another aspect is to reduce the indium consumption. With this, we are working with CNS and with von Arden to reduce the TCO, especially on the rear part, but also we are working to introduce a part of a multi-layer in which we include EZO to reduce the costs. And then other aspect is the soaking. We have developed, we have in our line the light soaking that has been developed by Applied Materials in collaboration with CNS during the development. We have implemented this on the line. We can increase the efficiency, especially we can also tighten the distribution by improving the efficiency of the lowest efficiency cells. This tool has been developed using LED by Applied Materials. It has been designed and then has been proven at CNS and then implemented in our line. Today, we have this tool in manufacturing. The silver, as I told, silver is a very important aspect. The amount of silver used in PV is increasing a lot. We need to reduce the consumption of silver, especially for heterojunction, that we have a large consumption of silver. So we are using silver copper paste to reduce the consumption of silver. We have started with silver at 40%, but we want to achieve, sorry, we started with silver at 60%. We want to go to less than 50%, and even our target to go to 40 or 30% amount of silver in the silver paste usage. Coupling the silver paste with the zero bus bar, we can advanced assembly technology, we can reduce very much the use of silver. There are some companies that today are starting using even let's say less than 50% of silver, has been already shown. We think that with this we can, let's say, fill the gap between heterojunction and TOPCon technology, and so we can reduce very much the costs. In the future, we are developing a sort of localized plating, electroplating with the rice technology.
Cosimo, yes. Could you please finish in a minute?
Yes. And this is to put directly copper on the solar cells. As this has been already shown, we are using today it's commercial, that is downshifting, in which we can block the UV, but also we can convert the light and convert the UV in visible light that can be used by silicon. So we increase the efficiency and we improve the reliability of the solar cells and the module. This is the roadmap of heterojunction. We think we can achieve the practical limit of 27%, starting from production that is around 25%, between 25 and 26%. We can, introducing this implementation, we can improve the efficiency. But the future is the tandem. Tandem is a very strong, let's say, target objective of our R&D. We are developing together with the CNS. We have started in the years from around 25%. Today we are achieved around 30% on an extended area that is not the full area of the wafers, but it's not a dot area. With this, we are now trying to shift and to convert a transfer to large area in our pilot line in Trisan. So we are targeting to introduce tandem as soon as possible and to industrialize this technology on a large area and using industry relevant materials for introduction of perovskite. I think this is all. Thank you for your attention.
Thank you, Cosimo. Thanks a lot. That's nice insights into what Trisan is doing. So unfortunately, I don't have time for questions, and please stay back till we again meet in the panel. There might be some questions in the chat window, so please answer them in the chat so that I will move on to the next presentation.
Okay, thank you.
Thank you.